So in this lecture we will see impedance matching network. So first of all, what is that? We will see here a network is inserted between a source and a load to achieve maximum power transfer is called an impedance matching network. So the network which is inserted between a signal source and a load to achieve maximum power transfer is nothing but impedance matching network. So the impedance matching is required for maximum power transfer purpose. So you might have learned this in the maximum power transfer theorem. So it can also be designed to provide a derived phase shift. So fine, in this lecture we will see how a T network can be used for impedance matching purpose. So for that particular function we will consider a T network. So this is T network, right? So this is the T network. So there is a source which can be connected this side, and there is a terminating impedance here. This is like load, and this side we will have source which is having some source impedance. Fine. So now we will see how this can act as impedance matching network, under which condition, right? So now let us say we have a source EG with internal impedance of ZG. Internal impedance is nothing but source impedance which is delivering power to a load ZL. Okay, in this case, for maximum power transfer, a T network can be inserted in between source and load as discussed follows. So if you observe here T network where there is no symmetry, that means Z1, Z2, Z3 are different. So for symmetry condition, mainly Z1, Z2 should be equal. So we are not considering them equal. That means it is for a generalized T network. So if you see, I am mentioning here load impedance and source impedance as image impedances. So we will see why it is like that, right? Okay. So as per this discussion, we are having a source EG with a source impedance of ZG and a load impedance of ZL, right? So to match the impedance for maximum power transfer, so I am inserting a T network. So for this particular purpose, let us see the condition. So first of all, what is the condition for maximum power transfer? We all know that Z Thevenin's of the network, overall network, must be equal to the load impedance, and this is with respect to magnitudes. Okay, so from this figure now, how to get Thevenin's impedance? So for obtaining Thevenin's impedance, we first remove the load and then we will short circuit the source, right? So that is only done here. When you short circuit the source, you will have only ZG here, and Z1, Z2, Z3 is nothing but T network, and then you have to remove ZL and it is removed, and the impedance seen from the load side is nothing but ZTH. So this is what is this. So now, so that means here we need to design Z1, Z2, Z3 such that this ZTH is equal to ZL. So that means when we have source impedance here which is terminated in this case, the impedance seen from the second port should be ZTH, which is nothing but ZL. So what is the other case in the original network? In the original network, ZL is the terminated impedance, and the impedance seen from the other port towards the T network should be what? It should be ZG. Yes or no? It should be ZG, right? Because the load seen from the source EG should be equal to ZG for maximum power transfer, right? With that condition, when load is terminated here, we are having a source impedance of ZG, and while determining ZTH, which should be equal to ZL, we have terminated impedance of ZG. So by observing these two, so we can say that these two cases are reflecting the image impedance concept. So this is, if we consider this as case 1, right? If we consider this as case 1, case 2 should be this one, right? So this is the condition or situation for maximum power transfer. That's why we can call Zi1 and Zi2 as load and source impedances for maximum power transfer. Due to this reason only we have introduced the image impedance, right? With this concept it has been introduced. That means the image impedances should be one of the load and source impedance for maximum power transfer, right? Yes. So these are the things which are written here. Now when Zg and Zl are image impedances, we can write Zi1 and Zi2 equals to these two equations, which are nothing but T network image impedance equations. And we also know that tan h theta is square root of ZSC2 by ZOC2, and tan h theta also we have. This is the equation because we have ZSC2 and ZOC2 here, which are substituted, and its ratio is substituted here, right? And since we have Zi1 equation here, Zi2, and from 1 and 2 if you multiply Zi1 and Zi2, it is the product. You will get Z1 Z2 plus Z2 Z3 plus Z3 Z1, right? Now if you consider this as equation number 4, 4 divided by tan h square theta. So what do you get here? You will get one equation, that is nothing but Z1 plus Z3 into Z2 plus Z3, right? So it is nothing but 4. What is 4? 4 is Zi1 Zi2. So Zi1 Zi2 is given there, right? So 4 is Zi1 Zi2 divided by tan h square theta, which we are getting the product of these two, which can be written like Z1 Z2 plus Z2 Z3 plus Z3 square plus Z1 Z3, right? Okay. Now if you consider this as equation 5, you do 5 minus 4. So from 5 minus 4 you will get this term Z3 square, right? So with this you can get Z3. So Z3 is nothing but Z3 is equal to square root of Zi1 Zi2 by tan h square theta minus Zi1 Zi2. So like this is the equation for Z3. This is for the maximum power transfer condition. So now we are designing a T network for the condition of maximum power transfer, right? Now if you consider Zi2 by tan h theta, you will get Z2 plus Z3. Okay, so then here Z2 will be Zi2 by tan h theta minus Z3. We already have Z3, which is in terms of known values, that is Zi1 Zi2, right? Fine. Similarly we can also get Z1. That means these are the designing equations or design equations for maximum power transfer, right? This is Z1, this is Z2, and this is Z3. Now we can assume some conditions here and get the simplified equations. So that means if we have these two assumptions, first assumption is Zi1 and Zi2 as purely resistive. That means internal resistance of voltage source and load as pure resistive. And second assumption is that Z1, Z2, Z3 as purely reactive. That means theta I is equal to J beta. That means the attenuation constant alpha is 0. So with these conditions or assumptions, you will get these values of Z3, Z2 and also Z1. So here you need to use some trigonometry conditions, which is like hyperbolic trigonometry conditions, that is sin h j beta is equal to j sin beta. Similarly you can also use tan h beta condition, where you will get tan h j beta is equal to j tan beta, which is given here. Fine. So with this we can conclude the impedance matching network, where we have designed a T network for the purpose.